The flammability of a plant community is affected by both its structure and by the species composition. When plants are more widely spaced, it's harder for flame to cross between them, either horizontally or vertically. And when plants are more or less flammable, then that affects the size and the duration of the flames that are trying to cross those gaps. Plant or leaf flammability is defined by three factors. These are the ignitability of the foliage, which is the time taken for a leaf to ignite at a certain temperature and the minimum temperature needed for that to occur. The combustibility of the leaf or the plant is effectively the size of the flame that will be produced by it. And the sustainability is the time for which that flame will burn for. Flames from burning leaves interact with each other when they are burning close enough together. So if we put two flames, say from two candles, close to each other, you'll see that the flames pull in together and produce a taller flame. In the same way, if you add one flame over the top of another flame, then we extend that flame length. So we need to know how densely leaves are packed within a plant crown. The two most influential factors that Frame currently considers in estimating the ignitability of the leaves are the leaf moisture and leaf thickness. Leaf thickness affects the surface area to volume ratio of the leaf. As a leaf is heated, moisture needs to first evaporate from it before the leaf can ignite. So more moisture and a lower surface area to volume ratio will mean that the leaf takes longer to ignite at a given temperature.
The most difficult measurement to get for leaves is the moisture content of the leaves. Here I'm using a moisture analyzer which measures the moisture gravimetrically. It means that the leaf is dried while being weighed, and the analyzer uses a very sensitive scale to determine when it's gotten to the point that it's not losing weight anymore, and compares the weight of water to the weight of dry leaf. I suggest breaking leaves, tearing them into small sections as I've done here, because as the leaves dry they curl, and if they're large leaves they will curl against the top of the machine and press down on the scale. If you don't have equipment like this or can't get measurements for specific plants, what I tend to use is some standardized values for most sclerophyllous vegetation. It's easy enough to just estimate at 100% oven dry weight. As plants become more mesic, we might call it 150 or 200%, until we get to rainforest species, which may be around 300%. In reality, they can be much higher than that still, but these are just very rough estimates. So we can measure leaf thickness. I use a micrometer about 2/3 of the way in toward the midrib of the leaf, and avoiding any veins that come out from that midrib, so we're getting the thickness of the actual leaf tissue.
Leaf thickness also affects the duration for which a leaf will burn, the sustainability of flame from that leaf, as does leaf width. So we look at the cross-sectional area of a leaf. A larger cross-sectional area of a leaf means that the leaf will burn for longer. In the same way, leaf width affects the size of the flame from the leaf, so that the surface area of the leaf, the length and the width of the leaf together, will affect the size of the flame coming from a burning leaf.
Within each branch, we can then take measurements for individual leaves. The first of these is the leaf length, where we're measuring from the point where the petiole joins the leaf to the tip of the leaf along the longest axis. The second measurement is leaf width, again at the widest point of the leaf. The first thing we want to estimate for canopy descriptors is the clumping of the leaves in the canopy. We can see how branches form clumps of leaves. In some plants this might be completely uniform, but in a lot of plants, such as many eucalypt species, we will see that clumps of leaves are quite sparsely separated. One way of quantifying this spacing of clumps in the tree is to look at the ratio of clumps to gaps in the canopy. This is not an exact measurement. It's a rough impression that you measure by looking at the tree from side on. So I've made these diagrams that you can use to get an impression of how much of the tree canopy is made up of clumps versus gaps. The next question is the size of the clumps, and again we measure that as the ratio of that clump size to the size of the canopy, and in this way it scales as the tree grows. We work with the assumption that the clumps stay at a continuous scale in relation to the size of the tree canopy. The next issue is the density of leaves within each clump. The first way to estimate this is through the ramification of branches. In ramification, we're looking at something that's similar to stream ordering, where we have a first order branch, which is the branch that the actual leaves are attached to. A second order branch is made up of two first order branches joining together. A third order is two second order branches joining together, and so on. If you join a second order branch to a third order branch, it stays as a third order branch. You just need two branches of the same order to go up another order. Leaves are attached to each first order branch with a given spacing, and you can measure that by measuring a length of first order stem and dividing that by the number of leaves along that length to give you an average separation in centimetres between leaves.